Welcome back, everybody. In this video, we're continuing with section 3.3. In the last video, we're working on power functions and a little bit about polynomial functions. Here, we're going to start by looking at the end behavior for a polynomial function. So for a polynomial, it turns out that the end behavior is going to be the same as the end behavior for the leading term all by itself. So what that means, or as an example, if we have this function, negative 2x to the fourth power minus 3x squared plus x minus 1, that this function's end behavior is going to be the same as the behavior of negative 2x to the fourth power. And negative 2x to the fourth power, the degree is 4, which is even, so both ends will do the same thing. And then they're both going to go downward due to the fact that the leading coefficient is negative. So the left end will go down, the right end will go down. Given that this is a polynomial, the middle part is not going to be as nice and simple looking as on a power function. That is, it could have some waviness and intercepts and all kinds of stuff going on in the middle. And at this point, we don't really care what that is because we're just talking about end behavior here. So we don't know what the middle is going to look like. That's going to depend on all these other terms. But as far as the end behavior goes, the end behavior will match whatever that corresponding power function will be. Okay, let's try one more example and then we'll talk about why it works that way. For this one, we have 2 minus x raised to the 7th power. And for this one, I'd recommend that you don't actually multiply this whole thing out because it's just going to take a lot of your time. Instead, we want to just think about what that leading term is going to be. So if you multiply out 2 minus x raised to the 7th power, all those, your leading term is going to end up being minus x to the 7th. And then you're going to have a whole bunch of x6 and x5 and x4 and so on. And then your last term is going to end up being a 2 to the 7th power, which is like 128, I think. So, but all that doesn't matter. What matters is that leading term, which is minus x to the 7th power. It's going to have an odd exponent, so it has which is odd degree, and so the two ends will do two different things. Since the leading coefficient is negative, that means that the right end will be down and the left end will be up. Again, we don't know what the middle part is going to do. The other terms will dictate all of that, but as far as the end behavior goes, that's completely dictated by that leading term. So I'm going to show you a couple of examples in a minute, but before we do, I just want to talk about why is it's okay to just kind of ignore all these other terms when we're considering just the end behavior. Remember that for the end behavior, we're looking to see what happens as x approaches positive infinity or x approaches negative infinity. Okay, so that's really big values of x, millions and billions and trillions and really huge gigantic numbers, like, you know, all the eyelashes of all the people in all the world. Okay, that's a lot. That's a big number. Okay, so if x is a really big giant number, and let's just take x squared and x squared plus 3x minus 5. Let's say we just want to consider these two functions. Okay, so if x is a really big number, then x squared is going to be even bigger, of course, right? If x is like a billion or something, then I know 3 billion is really, really big. But the thing is that x squared is so much bigger than that, that in a way we can just kind of neglect the 3x, even if it is kind of large. And we can neglect it because relative to the size of x squared, it is not as big. And then the negative 5 is really insignificant. If you had $3 billion, then you could afford to give somebody 5, right? If $5 falls out a hole in your pocket and you've got 3 billion, you're not going to probably notice that 5. Okay, so the minus 5 is relatively insignificant compared to the x squared and the 3x. Although, you know, again, if you have, you know, a billion squared plus 3 billion, 3 billion is a really big number, but a billion squared is so much bigger than 3 billion that in a way we could kind of neglect that 3 billion as well. So when x, the point is, when x is really, really large, that leading term dominates over the other terms to the point where uh, they're going to be relatively insignificant. Okay, I'm going to show you a couple of graphs that will also illustrate that, how that works. All right, so I want to show a couple of examples. So here on Desmos, I've graphed y equals x squared. It's in red, and then y equals x squared minus 4x plus 7, shown in blue. So you can see that the two graphs, of course, in the small look pretty different from each other. That is, on just that part of the graph, they look different. But if you zoom out, which is, again, what we're talking about when we're talking about the end behavior for a graph, they're both going to go towards positive infinity. And eventually, if I zoom out far enough, you're not going to be able to tell the difference between the two functions there at the end. So the end behavior of the two graphs is going to be the same. That minus 4x and then definitely that plus 7 don't really do a whole lot. Even if I make that -4 into like -14, of course, in the small, it's going to look like the two functions are different. But if we look on a large scale, really big values of x, it's not going to change very much at all. Okay, let's take a graph function that is a little more complicated, like x to the 7th power. Okay, let me make it a little smaller than that. Let's do just x cubed, actually. And then all right, so there's our graph of x cubed. Let's add to that something fancy looking. Y equals x cubed minus 14x squared. Now those look really different, right? Plus 3x minus 5. Okay, so there we go. Those two functions look really different, right? The x cubed shown in red, and then this other one, x cubed minus 14x squared plus 3x minus 5 in green. Of course, the two functions there look totally different from one another. We know that y equals x cubed will be left end down, right end up. Let's see what happens if we try to zoom out on this function. This one, it's going to be a little bit hard to tell because of the growth rate. So let me change some of the scaling real quick. All right, so that's too far. Okay, so let's see if that looks better. Okay, so here, looking kind of close, the two graphs look different. The green one has definitely a more of a wiggle than the red one has. But in the ends, which is of course where we're going for end behavior, they're going to end up going in the same places. That is, the left end will be down and the right end will be up. Let me see if I can add a little bit more wiggle to that. Okay, that's x to the 9th. Let me make this an x to the 9th. Okay, so that's a little too much. Okay, so there's a 9th power polynomial. So again, if you look close, the two functions look different from each other, but their end behavior is going to be the same. Left end down, right end up. So the point of these examples was to illustrate that if you have a polynomial function, its end behavior is going to match the end behavior on its leading term, because in a way, their lower degree terms get relatively insignificant the bigger the values of x are. Okay. All right, so let's continue with section 3.3. We just got done talking about end behavior. And so what we're going to do now is continue talking about some of the qualitative aspects of graphs, like their turning points and intercepts. So a turning point of a graph is a point at which the graph changes direction from increasing to decreasing or from decreasing to increasing. An easy example of that is going to be if you think about a parabola. Right? A quadratic functions graph is going to have a minimum at the vertex, like as shown here, this one will have a minimum at the vertex, as we've discussed. The graph changes from decreasing to increasing right at the point hk. Okay, that's going to be a turning point for the function. Okay, so if you have polynomial functions in general, we only had a vertex for a quadratic function, but any kind of polynomial function is going to have turning points that you're not going to necessarily call them a vertex. Vertex really is just applied to quadratic functions. But each of these would be turning points because they're points where the graph changes from increasing to decreasing or from decreasing to increasing. So those are turning points. Okay, the y-intercept is the point at which the function has an input value of 0, that is where it crosses the y-axis. The x-intercepts are the points at which the output value is 0. So as examples, that's a y-intercept. And there's 1, 2, 3, 4 x-intercepts. Okay, so there's several turning points. 1, 2, 3 turning points, 1 y-intercept, and 1, 2, 3, 4 x-intercepts. For y-intercepts, the input value is 0. For x-intercepts, the output value is 0. Okay, if we're given a function in factored form, we want to see if we can figure out some of these features. So we're going to first determine the y and x intercepts of this function, x minus 2, x plus 1, x minus 4. So we know that the intercepts will occur when there is an input, when there is, the y, let's go with the y-intercept first. For the y-intercept, that is going to correspond to having an input value of 0. So f of 0 will be 0 minus 2, 0 plus 1, 0 minus 4. So that will be negative 2 times 1 times negative 4, or positive 8. So the point will be 0, 8 for that y-intercept. For the x-intercept, that's where we get outputs of 0. So the polynomial here is going to end up equaling 0 if one of the factors is 0. That will occur if x is 2, negative 1, or 4. So at x equal 2, x equal negative 1, or x equal 4. So there's 3 points, 2, 0, negative 1, 0, and 4, 0 will all be x-intercepts. Okay. For turning points, the number of turning points and intercepts is related to the degree. If you have a polynomial with degree n, it's going to have at most n x-intercepts. It could have fewer. It'll have at most n x-intercepts and n minus 1 turning points. So example, let's start off easy at first. So a linear function, y equals 3x plus 1. Okay, that graph is going to be a straight line, right? And here the x-intercept is going to be negative 1/3. The y-intercept will be 1. So the graph looks something like that. Okay, for a linear function, how many turning points is it going to have? How many bumps? None, right? If it's straight, and think about it, this thing has degree 1. 1 minus 1 is 0. So it's going to have 0 turning points. Okay, it can have at most n x-intercepts. This thing has degree 1. It's going to have at most 1 x-intercept. For a quadratic function, that's degree 2, right? 2 minus 1 is 1. It will have to have 1 turning point. And it can have at most 2 x-intercepts. This one drawn here has 0 x-intercepts. This one has 1. And this one would have 2 x-intercepts. With a parabola, is there a way to draw a parabola graph so that it crosses the x-axis 3 times? or more is not possible. And that's basically what this is saying, is that the number of turning points will be always one less than the degree, and or less, and then it will have n turning points or n x-intercepts at most. All right, so let's just try this graph real quick. This one, we want to find the minimum degree of this function. The degree, of course, could always be higher, but it has 1, 2, 3, 4, 5 x-intercepts. So the minimum degree is at least 5. It's going to be at least 5. And then how many turning points does it have? It has 1, 2, 3, 4. Notice that that is one less, so one fewer, right? Okay, so the minimum degree is at least 5. The number of turning points was 4. All right, so we're almost finished with this. So the graphs of polynomial functions that have degree 1 are lines, linear functions, right? We talked about that. For degree 2, they're parabolas. Higher degrees, we've seen that they're more complicated graphs. It turns out that all of the polynomial functions that we've been considering are what's called continuous. What that means, there's more on this in calculus, a more official way of looking at it, but basically you can think of it as, are you able to draw the whole graph without lifting your pencil or not? Okay, so all of the polynomial functions, you could draw the whole graph without lifting up your pencil. Ways in which a function can fail to be continuous are shown here. This, of course, not applies to polynomial functions that are everywhere continuous, but for non-continuous or discontinuous functions, it may be because they have what's called a jump discontinuity. We saw examples of this with piecewise defined functions. If it looks like the function values are headed to a particular spot and then suddenly they jump up or down to some other place. A removable discontinuity, it's called this because you could actually remove the discontinuity just by changing one function value. Okay, the jump discontinuity, you wouldn't be able to kind of patch the hole by plugging in one value or fixing one value. Okay, that's the difference between a removable and jump discontinuity. A infinite discontinuity, on the other hand, is a function or a discontinuity in a function where the graph is either approaching positive infinity or negative infinity in the middle of the graph. We saw functions approaching infinity or negative infinity in our discussion of end behavior. Here, a function could approach infinity somewhere in between. And when that happens, you get an infinite discontinuity. Okay. Also in the section, we discuss a smooth curve. What it means for a function to be smooth is that the graph doesn't have any sharp corners. For example, all the polynomial functions we have are smooth. In particular, this example, x cubed has a nice smooth graph. The absolute value graph, the cube root, fifth root graphs, graphs like those are going to have sharp corners at the origin. Here, this one has a sharp corner at the point 1, 2. All right, so this finally takes us to the end of section 3.3. Let me know if you have any questions, and then have a great day.